Hey everyone, I'm Ankur, and I'm a grad student in the AMP lab and interning at Databricks for the summer. I'll be talking about GraphX, which is a library for graph computation on Spark. All right, so graph structured data is common in analytics. For example, you might want to analyze the link graph for Wikipedia. So there you'd parse the XML of it, extract the link graph, maybe run PageRank on it, and get a table of the top 20 pages, for example. Or you might extract a term document graph and infer the topics associated with each word. Or you could extract a user edit graph and find maybe the communities of Wikipedia editors. So let's look at one of the graph algorithms, maybe PageRank. PageRank identifies well-connected vertices by iteratively updating each vertex's rank using a weighted sum of its neighbors' ranks until convergence. And that's what this formula shows. And these ranks can be updated in parallel. So there's the rank of user I is updated by using the weighted sum of its neighbors' ranks. And here's what one step of PageRank looks like for one vertex. Here, each edge is first of all weighted inversely by the out degree of its originating vertex, which ensures fairness. And the update operation looks at the neighborhood of the red vertex, for example, and performs the weighted sum, which yields the new PageRank. So it went from 1 to 3.65. And the same operation occurs in parallel at all the other vertices as well. So here's another graph algorithm, single source shortest path. What this does is it finds the distance from each vertex in the graph to a particular source vertex. And here the source vertex is marked in red. And we can find the distance from each vertex to the source vertex by, in parallel, by first setting the source vertex to have distance 0, since, of course, it has distance 0 to itself. And then by iteratively updating each vertex's distance to be one more than the minimum of distance of its neighbors. So like PageRank, each vertex here can do the update independently using its neighborhood. And for example, the central vertex here maybe will do this update by receiving its neighbor's current distances and taking the minimum of them, and then adding 1. So now it's 2. So it's 2 hops away from the source. And then that process repeats in parallel again until the distances have converged. So these parallel algorithms have something in common, which is that their parallelism exploits the graph structure. In particular, graphs are parallel over vertex neighborhoods. Graph algorithms in general might have some centralized state and might have some state on each vertex and edge. And so for example, the page rank of each page is state. The current best distance to the source for shortest path is also some state. And for other algorithms like ALS, which Amit mentioned earlier, the user or movie's feature vector can also be expressed as a graph algorithm. So then in each iteration, the update to a vertex's state depends only on its neighbor's state from the previous iteration. And this enables each vertex to perform its operation in parallel. And so this graph parallel pattern actually captures a variety of algorithms from machine learning, data mining, and graph analysis. So a variety of graph parallel systems have arisen to support that pattern, including Google's Pregel, there's Giraffe, and GraphLab. And these systems expose specialized APIs, first of all, that let users express computation that fits that graph parallel pattern. And they also implement specialized abstractions specialized optimizations to enable them to run much faster than general data parallel systems like MapReduce. So first of all, a common specialized graph API is the Pregel abstraction. And this lets users write vertex programs that run in parallel on each vertex and then that send messages to neighbors. So for example, PageRank in Pregel, this consists of 3 steps. First, receiving messages, the rank contributions from neighbors. Second, updating the rank of the current vertex to incorporate the rank update. And then third, sending back the rank updates to neighbors for the next iteration. So specialized systems are attractive not only because they provide a well-suited interface, but also because they're fast. They build indexes in memory, and they lay out the computation of the graph to exploit the graph structure. That makes them much faster than performing the same operations using standard data parallel operators like join and group by. So for example, here's a performance example where MapReduce takes about 1,300 seconds to run PageRank on a medium-sized graph, and Spark, which is another general system, takes it's 4x faster, but a specialized graph system is 16x faster than even that. So this is why specialized graph systems have so far been attractive. But there's one shortcoming of these specialized systems, which is that real graph analytics isn't just about running specialized graph algorithms really quickly. It actually involves multiple views of the same data, both as graphs and as tables. And currently, we need separate systems to support each view. Hadoop and Spark, on the one hand, support table-based analytics operations, things like map and group by, and GraphLab, Graph, and Pregel operate on graphs. Now, having separate systems for each view causes two problems. First, it forces the user to learn, deploy, and manage multiple systems. So that's an operational complexity. And also, to share data between those systems, it requires the user to move the data across the network and file system, for example, by reading and writing it to HDFS. And also, different systems might build the same indexes over the data, but can't reuse that shared work across systems. So GraphX aims to address that problem. First, by introducing a new flexible API that can operate on both tables and graphs, and by incorporating that API as a library that uses graph parallel techniques to be as fast as specialized systems. And by embedding the graph parallel model within Spark, GraphX can integrate easily with RDDs and can perform data parallel operations while also enabling the speed of specialized graph systems. And so the goal is to enable users to express the entire pipeline within Spark without requiring data movement between multiple systems. And this has been a common theme, of course, for a lot of the sub-projects of Spark. Now, the key to this is that graphs and tables are really just views of the same data. And switching between those two views, table and graph views, gives access to more appropriate operators, and it also hints to the system a way to optimize the execution by giving it information about the semantics of the data. In particular, you can view a graph as two tables. A vertex table that associates each vertex with a property, and an edge table that associates each edge with a property. So here, the top one is the vertex table, and the bottom one is the edge table. And so we embedded GraphX into Spark, which provides the table operators for us, and those are familiar too. And we also introduced a set of graph operators to do things like viewing RDDs, tables, as graphs, viewing graphs as RDDs, and computing things like PageRank. Plus, there's some convenience functions that just run the appropriate RDD operation on the vertices or edges, such as map, join, subgraph, and so on. All right, so to summarize, GraphX is a library on Spark that allows viewing the same data as both tables and as graphs, and that provides a graph computation API that can express a variety of algorithms. And here are some of the ones that we already have contributed by users, many of them. And this enables all kinds of exploratory analysis to take place from within Spark. So now I'll go into a bit more detail about the abstraction that GraphX provides for working with graphs, as well as how it's implemented and how that ultimately performs, whether or not it's really competitive with specialized systems. All right, so the two essential operators that GraphX adds are triplets and MapReduce triplets. So the triplets operator, first of all, it joins the vertices and edges, bringing the vertex properties, those are the things in blue, together with the edges where those vertices are referenced. So here on the far right-hand side, there's a triplet, which represents the joined view. And then based on this, the MapReduce triplets operator takes that and uses it to perform neighborhood computation, as PageRank and shortest path, for example, require. So the neighborhood of a vertex is just the set of adjacent triplets, because the triplets also contain the neighboring vertex attributes. So we can compute the neighborhood, compute on the neighborhood by summing the triplets using map and reduce UDFs, and that yields a new value for the central vertex. So this MapReduce triplets operation captures, as I mentioned, a bunch of graph algorithms, and here's a small example or a small visualization where we're computing just in the neighborhood of the vertex A. So here the map function runs on the adjacent triplets to A. Here just the in edges, but we could run on just the out edges, or both in edges and out edges, and so it produces some results. And then the reduce function sums the results of the map function and yields the new value for A. And of course, we can use this to express a bunch of algorithms. Plus, here's a simple example where we're just trying to find the age of the oldest follower for each user in like a Twitter social network. So there, each user is a vertex here, and it's annotated with each user's age. And what we would do is we would to find the age of the oldest follower, we could take the age of each follower in the map function and send it to the user being followed. So I don't know if you can see, but so e.dest.id means to send something to the user being followed, and e.source.age means to send the source of the user, the age of the user who is following. And then we could just take the maximum such age, that's the max function, as the reduce function, to take the maximum age of each follower for each, or maximum follower age for each user. All right, so now let's just briefly talk about how GraphX really represents graphs on the cluster and computes on them. So GraphX represents graphs using a particular layout that lets it handle graphs with high-degree vertices, which is hard for other systems like Giraffe. So now, on top of that layout, MapReduce triplets can operate. And since that's the key operator for graph computation, we focus on making it fast, especially for iterative algorithms where it's called repeatedly, and where the graph is updated maybe based on the result. So, and then finally, I'll show how all this work makes GraphX competitive with specialized systems. First of all, here's how GraphX lays graphs out on the cluster. First, it takes a graph and represents it using two RDDs, the vertex RDD and the edge RDD, as I mentioned. So vertices are stored as pairs of vertex ID and vertex attribute. So here, this is a vertex table that stores vertex attributes. And the edges are stored in a separate RDD from the vertices. And that implies a vertex cut layout, where a single vertex might have neighboring edges on multiple machines. So here's the vertex and edge table. And the scheme allows the system to support high-degree vertices easily, since we can just balance the edges across machines using some, for example, hash partitioning function that distributes them evenly. We can do this regardless of which vertices an edge connects to. So now, based on this, forming the triplets view requires that each edge partition be sent the vertex attributes of the neighboring vertices. And to facilitate that join, here's the join that we want to do. And so to enable this, we introduce a separate data structure called the routing table, which describes for each vertex attribute which edge partitions it needs to be sent to. So for example, here, vertex A is mentioned by edges in both partitions. So to form the triplet view, it needs to be sent to both, whereas vertex B is only mentioned in the first partition. And so there's only partition 1 there. All right, so now once the vertex attributes have actually been sent to the edge partitions to form the triplets view, it makes sense to cache them there in case the user or future iterations need to access the triplets again. So the vertex attributes are stored in a cache at the edge partitions. That's the mirror cache there. And now a call to MapReduce triplets works by scanning the triplets on each edge partition and running the map function on each triplet. And that yields the calls to the map function produce results that can be aggregated locally, first of all. So they're the local aggregates. And then those aggregates can be sent back to the vertex table for the final aggregation. So here's how this whole MapReduce triplets, like one stage of a graph algorithm proceeds. Now we made some important optimizations to this pattern to make graph computation faster, but I won't go into detail on those. Suffice it to say that I've talked about them in past talks, so I can send you the slides if you like. But the result is that GraphX performs pretty well. So here's how it performs. First, we ran this benchmark on a web crawl of the .uk TLD, so it's a web graph, with 3.7 billion edges. And we used Spark to write a naive data parallel version of PageRank, and also another algorithm, connected components, which figures out how many graph components there are. This serves as a baseline. So if you want to do graph computation within a flexible system like Spark, then it's going to take 8,000 seconds for PageRank, for example, and even longer for the other algorithm, where it actually hadn't finished the first iteration by that time. So we killed it. Whereas if you just want to do graph computation without any pre-processing, post-processing, or general analytics, then a specialized system like these ones will be an order of magnitude faster. So GraphLab here is 10 times faster than Spark approximately. And Giraffe actually is also fast, but it crashed in the other version because it ran out of memory due to lacking this vertex cut optimization for high degree vertices. But GraphX provides comparable performance to these specialized systems while also providing the flexibility of Spark. So that's the pitch. And you'll get a chance to try out GraphX later today. One of the exercises is to work with Wikipedia data. And so here, there's sort of a pipeline that you would do. I've done the first 3 steps there because they involve processing a large amount of data, which you can't fit on your USB drive. But you'll get to run PageRank and take the top 20 pages. All right, finally, there are several interesting directions for the GraphX project that we're looking into next. One of them is computation on time-varying graphs. So existing graph systems have tended to focus on static graph analytics, where there's just some existing graph that all you want to do is get results like PageRank. But in fact, real graphs tend to change. The web graph, for example, links and pages get added all the time. With social networks, people make new friends and so on. And there's been a lot of theoretical work on incremental graph algorithms that can efficiently accept updates to the graph. But as far as we know, nobody's implemented those in a distributed setting. So we're interested in making it easy to express those. And I'm actually actively working on this, although it'll still take several months for it to be released. Second, GraphX focuses on batch iterative graph computation, while there's a separate category of systems like Titan that focus on graph storage to optimize point queries. And these are complementary roles. So one interesting idea is to provide a Titan-like interface over data stored in GraphX or processed on by GraphX. And finally, graphs might be stored in a compressed format on disk or on memory, and it would be worthwhile to operate directly on that compressed format. And in fact, GraphX can do this it has a special capability because it doesn't rely on random access to the edges. It just needs to scan them sequentially, as you might recall in the map reduce triplets diagram. So it actually could support operating on compressed data. All right, so that's all I have. Make sure to try out GraphX in the tutorial later on today, and go ahead and check out GraphX online as well. Questions?
When GraphX traverses a relatively complex graph, goes from node to node in the cluster, will the cluster shuffle the data around?
Okay, so the question is, when GraphX traverses a complex graph, does that require any data movement, any shuffles to do that? So the answer is yes, because vertices are split across multiple partitions typically. There is some computation that's involved in communicating between different parts of the graph that have been partitioned. So that's unavoidable. But yeah, we try and minimize that first of all by partitioning the graph cleverly. And also, many operations don't require data movement. So things like if you have an existing graph and a derived graph, and you want to join those two, that's a very cheap operation. But yeah, some things like neighborhood computation do require data movement.
I read a few papers probably like 3 months ago, and it was showing, according to reference data sets, that GraphX is about half the speed of graph. That things change or not change.
So the question is about performance discrepancies. So many benchmarks have shown GraphX to be somewhat slower, so 2 or 3 times slower than the fastest systems like GraphLab. So that's true. That's a very good point. Those benchmarks, I should have pointed out, they're actually based on a version of Spark that's been optimized for GraphX by using in-memory shuffles. So it turns out that when shuffling large amounts of data, on EC2 especially, the disks can have a high latency just for doing any kind of simple access to them. And so we used memory for shuffling for GraphX, but we haven't actually released that into Spark since it's kind of a messy change. Yeah, so that's true. With stock Spark, you'll probably get a 2 or 3 x slowdown versus the fastest specialized systems like GraphLab. Oh, yeah. Follow-on question is when will we expect that the optimizations to come into Spark? Well, that's one of the things I'm trying to do for the summer. So hopefully by the end of the summer, we'll have those into Spark. All right, thanks.